start on this. All right, we'll go ahead and get started. So today I'm going to do a review session in preparation for the exam on Thursday. We will have an in-class hour, 15-minute exam. And we will focus on all the materials throughout the course. You can bring a sheet of paper for like front side only for like a note thing or a formula sheet. You can make your own sheet. You can bring your basic calculators, but we're not going to use any computers or any notes, anything like that to do the exam. Today, I posted a sample exam from last semester on the course site. And today I'm going to go through some slides that kind of solves those questions there. And I haven't made the exam yet, but I'm going to probably make that tomorrow there. So look through that and kind of work through those problems. And I'm going to go through some things today, through the whole course, and I'll slow down with some stuff that I think is important. But that's the idea of today's lecture here. So we started out with just talking about automated processes, and then we started getting into sensors and actuators, and then we started using PLC control, and then we got into robotic manipulators in the course there. And so just know the basis of industrial automation in general. What's the purpose of industrial automation? I'm really just trying to automate different tasks, electrical, mechanical components together, and it's going to involve sensors, actuators, and usually some kind of closed loop system to have some input. Given the input, you're going to have some desired output, and you're controlling some kind of process. In this class, we're using the PLC to that, but you can also have embedded controllers. You have all different types of other controllers too as well that we're not talking about in this course here. But there is a process that we're trying to control in some kind of fashion. Is the kind of the elements or the main objective of this course. In this course, we were trying to use more of the smarter automation, adding sensors, IoT to do those things in the traditional. You could do everything in this process control using relays if we want to, and some kind of timing sequence, but we're going to try to use more advanced control algorithms to actually do that process, use some kind of control system in this course here. And so this is our basic feedback control loop. We're mostly using closed loop in the system. So you have the controller. In this case, the controller is, we're mostly using like a bang controller. We're turning the conveyor up off, we can tailor it off, or we actually use some timers. If we actuated a DC motor, and then we went through some kind of, the process was the actual system itself, and then we had some feedback loop there on the sensor encoder, and we talked about different types of sensors in this course as well. So that leads into the next point. We need sensors to control our system, our process there. And so it's and the sensor is going to have certain characteristics, and that's where we're going to get to more on the exam, knowing what the noise, the linear area of the system, the sensitivity, the range of the system, and those kind of things here, and the definitions of those as well. But we talked about different types of sensors for that first homework. We had giving an ultrasound versus just different. Given a certain material property, was metallic. What would be the best sensor to use for that particular application? There's multiple answers to this, but there are some wrong answers too as well. Like a limit switch, if you're trying to detect something, they have to actually make physical contact with that. But we mostly be using proximity sensors in this course to do different things with the conveyor belt system here. And we didn't really use the electrical mechanical relay, but it's just going to turn things on and off. And we're replacing that with the solid state sensors. And that's what we use in the lab 1 through to lab 3. It's these solid states sensors here. So the key takeaway here is just knowing the different types. Just maybe review the inductive versus the other kind of magnetic and capacitive, and just know the pros and cons of those. And know that we talked a little bit about the MPN and the PNP, and that's common for manufacturing automation. These are the two most popular sensors here, but it's going to be one's going to be like normally open, one normally closed, depending on the wire there. But it's a p-in junction, a solid state sensor system here. I'm going to move fast through some stuff that may not be as important. Just basic theory here, but nothing that's too exciting. Here is something that maybe want to slow down a little bit here. We could make a model of all these blocks, and that's where I do more of the digital, modeling, where everything kind of the digital twin of different systems here. So you can model a control system, you can model the process, you can model the actuator, but you can model the sensors, and most of these sensors want to be a linear system. So you want a y equals mx plus b. In this case, it's the s equal the c plus ms plus b. So it's a linear function given the input s, the output the lowercase s, the output s is going to change, but it's a bias called c, and then you have some kind of slope m, and you want that slope to be a nice ramp that you have some given the change in input, you will have a measurable change in output, and that's what makes a good sensor there. And so that m, knowing that m relationship or be able to compute that is important for this concept here. And there's going to be a sample question that maybe looks like maybe like something like this here. So go through here. Given the output of the sensor is given in 12 milliamps, and this is so you got the two unknowns. I mean, enough information to derive that linear relationship. And then you'll be able to give you the sensitivity, okay, ask what is the output of this particular input there. And so review this here in preparation of your exam here. And then the answer is actually on the next page here, but it's really computing the sensitivity of a sensor. And maybe just given some different numbers here or given something else. But look into this for a review and for your exam here. And also we talked about precision versus the error here. So just kind of maybe know some basic definitions. But here, computing the error, we had a homework assignment with that here. So giving the error is also going to be the measured minus the actual value. So note that relationship here. It's not the other way around, or you have a sign error. And we talked about the mu is the mean here, and your sigma is the squared. Sigma squared is the distribution here. The smaller that the better ideal sensor it is. The larger distribution in that sigma squared, the more noise it has in that Gaussian distribution there. But you'll be able to, given a real sensor here, what is the best sensor for that particular operation? So I may give you a couple of the sensors. Choose the right sensor for this application and tell me why you chose that particular sensor. And then you can look at maybe the error of that sensor at that particular distance, if it's in the right range, or it may be something, maybe give you the plot. You're not going to actually do any plots or anything, but I may give you this system here and say, why is this system better than this here? Why this sensor is better than this sensor at that particular range? And just describe in 50 words or 100 words why you chose that sensor. And in this example here, given these two sensors here, you can see that as the distance increased there, the noise gets a little bit larger. So it has a certain operating range there, and you could be able to pick the correct sensor for that ideal range. And then we have some other definitions of accuracy and then nonlinear error here. These are a little bit more harder to give on the exams because we do require a little bit more computation. But you could solve these using computer systems, pretty simple. Because we do some certain fitting algorithm here. And I showed you how to do this in using Python and MATLAB. But sensitivity is key here. Is just your change. Given a change in input, what's your change in output? So it's the slope of the system. So be able to compute the sensitivity of a system. and why, and is this better slope than going to 45 here? Is it better to go this way or a higher slope here, given that particular characteristics what you're looking for? And then we got into the system response, the first order.
Can you back up to where you said what slope is better?
Yeah, so for example, if I did, given the application, and so if I could have a sensitivity that maybe look like this here, and I could have something that goes up here. So a get sensor is given a change of input, and this is my inputs down here, and this is my output here. I would like to have a nice change in output there for a full range of the sensor. So if the range of the sensor is just from here to here, then this is okay here. But if this is my full range, so this is my, if it's an 8-bit sensor here, this is 255 here, and this is 0 here. And this is my sensor 1 and sensor 2 here. In this case here, that this sensor 2 may be a better fit. It's going to use up my full range of that and in my analog digital converter for a given input. If my input is in this range here, like if it's, so you can see anything past here, I'll not be able to actually measure that. So I would like to say giving a input of X units here, let's say this is my sweet spot here. What is the better sensor for that? System 1 or sensor 2? Does that answer your question? Yeah. And in this case here, the sensor 1 is probably, I drew it put outside of that, the range of that sensor 2 there. So I got a concept question. And then we talked about, this is the first order system, which is most, this is getting more to the output there. So it has this nice curvature that looks like the red curve here. We're really not gonna go into the definitions in this here. This is the time domain if you plot that over time, but we do need to know what tau is, and also like your steady state gain value here. So this is what GFSS here. So this, given the input response, which is a step response of 0 to 1, you had a change here, and most systems could be described as a first order or second order system here. It ramps up at a certain rate, and at 63.2% of the final value, that is my tau value of the system here. And that's what, if you measure that time there, that's what tau is. And then it goes to and it settles at your value here, which is your GSS of the system here. And that's also equivalent to in the Laplace domain here. So a sensor or a plant model we may call GFS for plant has a generic function in the Laplace domain of GFSS over tau s plus 1. And that looks like the same in, if you plot it in the time domain, it looks like this here. And so this is going back to modeling every single block as a transfer system here. And so I have some questions on the here. So what is the time response of the system, the Solon time and things like that, giving the actual plot to be able to read that. But more specifically, there's giving this particular model of a system here. What is the, if I want to do a transfer model of this system here, what is my steady state value of this system? It goes to 35. So 35 would be in my, for a step response would be there. And then I have tau s plus 1. And so, and this is called G of S. And so what is tau in this situation here? It would be 63.2% of 35. And so that's why you would be able to use your calculator to figure out that number. And that's 33. Well, I can't remember. It's on the next slide. I think. Yeah, 22 point something. So that's about here. And then I go down. And so that tau is about 125 there. And you'd be able to model this particular system response as a symbol link and something as this block here. So that's. And then we also talked about encoders. So as the light goes through there's going to be some kind of, it's going to block the light or like the light pass, giving some kind of pulse. And you'll be able to count the number of pulses, given the radius of the disc, know the, and this goes into like the linear actuators, those people using the conveyor belts for their project. If I want the conveyor belt to go to X distance and it has an encoder there, I could count the number of tits and that's equal to a certain amount of distance in your system there. So given the encoder size, the disk size, and the finer resolution there of the system. And so we view this particular problem here. We haven't done it in a while. And then if you're using the conveyor belt for your project, you may want to figure out what has an encoder in there. You may want to figure out what's the size of that encoder by going, actually looking at the number of tits and looking at the distance and figure out back computing the radius of this thing. And so this case is just computing the distance per pulse. So review this here for your exam. And I think that was one of the questions that was on that practice exam. And you have to either floor or cylinder that because you cannot have a half a pulse. It has to be a whole number. So just remember that. That could be like a -1 point or something like that if you have, don't do that. And another difference between the binary and gray code, do you remember the difference between these two encoders? So one has, this here has going from 000 to 001. You see we have 1 bit change here. So this is only 1 bit change here. Here there are situations where this is a 0 is the white and a 1 would be a black here. So here it went from 0010, and there's multiple bit changes in the system could occur there, and you could have a race condition and be able to detect that change in the encoder there. So grayscale guarantees only 1 bit change when the disk changes. And then we started getting into the actuators. So here's some definitions here that would not probably be used on this particular course. But if we get into dynamics, we talked about the dynamics of DC. This is the actual velocity of the actual motor by giving the voltage. You have a current go through the system. That current's can call the armature to rotate at a certain velocity. And we'll be able to do the relationship of that, given the load system, what is the speed of that motor given the voltage of the system there. And so necessarily don't need these definitions here, but you want to know the basics of, as you increase the voltage of the system, what happens to the velocity of the system there, or what happens to the torque of the system. So what's the relationship between the voltage and velocity, and relationship between the torque and velocity of the system there. And then eventually I want to control the system. And in that case, we had a DC motor and we had a conveyor belt. We wanted to move slow, fast, and medium speed there. So we gave it a pulsing signal, a duty cycle to actually control that in one of the labs there. And by pulsing it, we get the average voltage, which is represented in red, is equivalent to the amount of time high or low of those pulsing cycles there. And we had so giving a small pulse, we had a lower voltage, average voltage, and given a larger pulse, we had a higher average voltage there. And we want to control at a different speeds. We want to say, I want to make half the speed there, then I will use 50% duty cycle, so I'm on half the time and off the time here. So giving the speed, what is the duty cycle that you need to actually move the wheel at a certain, maybe a question, something like that here. And so this is the example to kind of go through here. I think this was also on the review. Here we have the system goes up to, this is RPM here, and this is the time response. So what is the maximum velocity that this system can operate at? Yeah, so it could go to like 100 RPM, and that's given a 24 volt. I turned it on all the way on, and I just let it ramp at this time period, and it ramped up here. So this is my own time, and I could compute my tau of the system, but it went to 100. It ramped up to 100 RPM of the system here, and I want to say if I wanted to only run at 40 RPM. So this is 24 volts here. What voltage do I need to apply, average voltage, to operate at 40 RPM, and what is the duty cycle to do that in percentage? So this question is asking something similar to that, but guys, as it comes, I want the conveyor belt to operate at the open loop speed of this here, and I want to use my timer circuit on my PLC or clock to output to control that. What was that?
So we 40 by 100
You need to get the voltage first, and then you need to figure out, okay, what percentage of that gets in the duty cycle. I think it's on this here. So I was keeping it in duty cycle here. So in this case, but I could give you any missing parameter, and you could solve for something. So it may ask you, given this duty cycle, what's the voltage? What is the RPM or something, or any one of the missing component? So just know this relationship here between all three of these relationships here. And then we went into, okay, we actually want to control this using the PLC. So we started introducing certain types of circuit. And we just went through some basic and/or in this particular course, we didn't go into any really more complex and some simple, the basic and/or, nans and nors and stuff in this course. But we did some simple Boolean expressions. We didn't do any reduction things, but to be able to go through here, but actually implement this in the PLC, and you may be able to draw the circuit out. So what was this circuit look like if these were input coils, and you want to, and Y is my output to a motor, and I want to design a circuit to do this here. And so you might say, draw this ladder logic to represent this particular circuit. And there could be multiple solutions depending on how you do your thing here. And then we just went through some basic latching circuits as well. If you want to keep that input high, how you do that in ladder logic as well. And then we started getting into the industrial communication protocol. We just talked about two here, was the Modbus and the MQTT. Just know what the definition, what is a Modbus? You don't need to know the history of it, but how does a Modbus work? And what is the advantages of a Modbus versus the MQTT? What's the disadvantages of that? What is MQTT? What's what's the advantages and pros and cons of each one of the systems? Well, given this scenario, how would you design the system for internet? And then you just kind of write a short paragraph of how you would do that, given these protocols here. One of the things here is with the Modbus here, we could only send we have fixed packet structures here, and they could send one single bits as the call status, and we could send the 16 bits as holding registers, but we don't have, we can only send either one of 16 bits here. In the MQTT, we can send JSON messages, we can have more advanced structures there, and we can define how that payload looks and the size of that payload of the system here. And with MQTT, we can actually connect to multiple sources. We have a broker in the middle. So just know how these things work here. We have your clients there, they all connecting to this broker here, and they can be passing messages back and forth. But I'm able to communicate with more than one person using this broker system than I can with this Modbus system. It's more of like a client and server system. And then we went into the robot manipulators. Is the last where we ended up there. We talked about frame assignments. So everything has a frame associated with it. Even all the joints has a frame associated with their, if you want to draw everything out, there's frames on everything in the environment. And we want to know, where is this object? And most of the time I use DH. Where is this object located versus the base or the origin, or what you want to call that. And this is my end effector here, and this is my camera system here. I detect this object here, and I want to go grab that object here. How do I know where this object is with respect of the base of the system here? So go through that here. So we know where the end effector is, and we also know, we talked about later on the kinematics here. So these are joint variables, Q1, Q2, Q3, and so on for in degree freedom system. And I can compute the end effector location with respect to the base. So I know this here and pose here, and this is my starting off my base here, and this is my end effector here, and this is mechanically mounted here, so I know this relationship here. That's my lambda from my end effector to my camera, and the camera detects the object here. So camera to object here. Where is this? This is unknown, so what is this relationship here from the base to the object? And you don't necessarily do it with numbers for the exam, but just to drive this relationship here. And what is this relationship?
Base to, what is the?
To the end effector.
End effector.
Yeah.
End effector to camera, the camera.
Yep. And then I could ask you to do the other way around too. Where's the object to end effector here? I notice you're going backwards here, but you could also go through multiple other chain loops here. So I could go, so you could be writing this as a positive, the systems here, and you can also figure out negative things, so depending on if you're going which direction. And these are going to be a homogeneous matrix, which is also represented by T in a lot of us, which is a 4x4 matrix. And we can also invert these matrices here to go to the other side here. So that's if we wanted to go this way here. So everything has frames and they become homogeneous here, and this is the transformation properties here. And this is what I just did in that last example here. So given this graph here, I can ask you about where any of these relationships here to be able to just derive it or just write down the relationship here in a symbolic format only for the exam, and tell me where things are. And this is the same graph, it's just represented a different way. All right, so that is some things. And then we start to get into, okay, those really are homogeneous, which is a 4x4 matrix with a orientation part here, and a position vector T. So this is my T and this is my R of F. So F dot R, F dot T. And And we started to, you could, and this is that full matrix here. And so this is already the generic rotation matrix of a system. And you can compute, they always use right-hand rule in this, in robotics in general, but we always use, never seen a left-hand system. And so a positive rotation, you just put your thumb around the axis of interest and then you curl it, and that's going to give you the positive is actually going that direction there. And this is kind of the last homework problem. I skimmed through those already. And it seemed like everyone was moving the right direction on that. So this is giving a system like that with some maybe symbolic numbers here. I had to figure out how I would do that on an exam, but be able to compute some certain things with that, similar to the last homework assignment. And then if you want to go backwards, we use the inverse kinematics as the forward, but also we talked about the chain, and this is the an open chain method, meaning that is or some people call it clamp too as well. That means it's only clamped, it's only closed on one end here. I think Prem was asking earlier about closed chains methods, something like this. And you can do the same technique to do that here. And that could, if you're interested in that, I could provide you the lecture notes on that here. And we do that as parallel kinematics too. We've talked about one of the robots that actually uses parallel kinematics to move a drill inbit around in your system here. But this is an open chain system. And they also have closed chain systems here. And you go through if you're looking for a particular point of interest, the end effector here, you use geometry, that works well, but as the end degree of freedoms get heavier or larger, a lot of people use either the chain method, which is rotations and translations to describe where that end effector or that particular frame of interest is in the system. In this case here, given a configuration, you may be able to derive this relationship. So I may give you a robot that looks like, let's just say a Cartesian, let's just do prismatic link here. Let's go this way, and it's able to do something like this. What is the E of the system here? And you have to tell me how to, and I would give you the links of this. I'll just be like A1 or 1 unit length here. How can you describe that robot using these transformations?
All of those are transformations.
What was that?
Where you have it up and over and up, those are all the transformations.
Yeah, so this is prismatic. It could extend this way here. So this would be almost like an XY. I meant to go up here. So like this would be like an XYZ platform. So this is really not drawn correctly here. Let me see if I could. And I probably should draw it a little bit more 2D. XYZ. So I'm able to slide this way. This thing on the CNC machine, I have I could go X, Y, and I could go up and down with the tool there. And so it is a 3D free robot, but it's prismatic, but there's a 3 degree of freedom center and rotation there. And just go through the chain method to get to the end effector here. And this is just one way of doing it. There is several ways to do kinematics here. And this is the one, the simpler one that we use for this class here. All right, and this is one we did. This is the SCAR robot. We did this on the homework minus the last prismatic link here. And the inverse is just going backwards. Sometimes it's not possible to compute the inverse kinematics. If you're in the last homework, you cannot necessarily get to the goal, because it was it was all plain air robot, so you didn't have but 2 degree of freedoms, and they had to solve for you, it gave you a 3 degree of freedom problem, and so it was not necessarily possible to actually get there. But you use a bunch of different methods to do inverse kinematics, and one I did in the class was optimization, minimizing the error between where you want to go to that there. But you can also use just inverse homogeneous. Once you have the 4x4, you can invert. This is this matrix, and this is an example of with a homework I did a long time ago here. Given this T matrix here, what's the inverse of that T matrix here? And since it's a special homogeneous, the rotation component, you could transpose that. So it means the rows becomes columns, and columns becomes rows, and then you could take the transpose and do the dot product of the P, which is the position vector here, and you could get the inverse pretty simple on the without using the a lot of this GPU anything like that to solve for the inverse kinematics. And so that's and so I would go through. So on the site, given what I just said, I know this one was kind of hard to read here, but it went to around, let's say 57, 58, for example, here. So given this response, and I gave you the first order system equation here, like what is the GSS of this system here, compute the tau of the system here, and you'll be able to just go up here, it's going to settle at a certain thing here, you're going to find that, you're going to find the 63.2% of that value, and then figure out the time response associated with that, and that's going to become tau here. So this motor has a max speed. There's no way it could go faster than the it's 57 or wherever it saturates at there. And so that's my top speed of the motor system.
Things such as knowing that it needs to be 63.2%. Can we have that on our note sheet?
Yep.
Okay.
If we can't memorize that, then that might be one you put on there. Yep. But tau is always going to be 63.2% of the GFS. And so that's the steady state gain, the tau here of the system here. So now I know I'm maxed out at this speed here. So that's the fastest I can move my conveyor belt, but I want to move the conveyor belt at a slower speed. And so I'm going to use pulse width modulation. I'm only want to, this say it went to 60 RPM just to make the math easy. In this case, it didn't, but I want to move at 30 RPM. So what would be my duty cycle to move? It would be half, and which would be 50% duty cycle there. And if it took 24 volts to make it, what would be the voltage I need to operate at? Yeah, exactly. Yeah. So that's and that's going to be represented by a duty cycle of by pulsing it on and off. The average voltage seen by the motor is going to be 12.5 there. We usually use a capacitor to hold that charge there, so it's not sweeping down there. But in this case, it will still work. You'll still be able to see it move at a slower speed there. And so that's the same thing, maybe giving a different speed here. So it's not going to be as easy as just half. You have to maybe actually compute that duty cycle without just guessing that. But you'll be able to some basic concept question. So now the conveyor belt's moving at my desired speed. And this is still open loop system. I want to use my encoder to kind of know where that I wanted to stop at a certain distance. And so given my encoder setup, how many clock ticks do I need to tell the motor to stop? This is what question 3 was asking in this problem. So in this case, I have a 16-bit encoder, and I gave you the resolution here. And I think I was asking for the radius. Yeah, what is the radius or diameter of that little encoder? You could and then any units I can convert it over for the thing, but that's what question 3 is asked. And then if I gave you, okay, if you had a radius of this, what is the resolution required to get, if I want to stop in 1 millimeter accuracy there? So now I have my closed loop system. I have a motor. I'm able to pulse it with my PLC, and I wanted to stop it at a certain distance. Now I want to control the PLC to actually do some logic here. So I put a push button, I put some photodiodes, emergency stop here, and I want to design the software for the system here. And so this was just draw out the operation to, I wanted to start the button, I wanted to stop it, but I also want to have an emergency stop here with B or C here. And so figure out what is the correct logic to actually write it out. And make sure you read it carefully and actually work it out, because sometimes if you read this as and or and then actually do the math, and you just want to verify that it actually works out in your head at least there. So this is just drawing the actual ladder logic. And then I just gave you, and you also had to go and give the full expressions here on the truth table here for that here. And then I ended it up here. So now I want to have the conveyor belt stop at a certain position so I could pick it up and grasp it with my robot manipulator. And so this has a robot with a camera on the end effector, but also has a camera in the fixed camera system, and I detect the object here. I want to know where the object is located just to verify it's in the right spot for the robot, so the robot can grasp that here. So where is the object located with the respect of the base of my robot system? And so we do the same thing we just talked about. We find that relationship here, which is the dotted here, and you'd be able to compute that with respect to the origin here. So I want to be able to get to this object here, and then figure out the relationship here. And so that's what 5 was asking. And then I want to be able to control the system over internet protocols here, so it's the MQTT or the Modbus. And so how will you, so each one of the questions is still building each other. How will you actually control the system here was the last question here. So it was a short essay format. And that was last year's. And so I'll probably come up with something different this year, but it's still telling the whole story for the whole class. Given this project here, conveyor belt system here, I want to do some things, and they're going to build on each other to a final questions. So I go through here, and if you have any questions on this here, I'm still be around tomorrow as well. So I could, if you want to work through this here and ask if you got it right or not, you could come by tomorrow or something like that. I'll be around. Any questions? Yep.
So say you said the questions are going to sort of build on each other. If we have a mathematical answer for one that ends up being incorrect, and it builds onto something else, are you just gonna?
Yeah, so that's what I did in number 3 here. I changed it. So I changed, so if there was this here, so if you got A around, then you can still do B, because I gave you, so this is not the answer for A, but I would say if this is the Will's thing was that, then you would compute another thing there. So I can't remember the actual answer here, but it wasn't 10 centimeters. And so I kind of changed it. So but I do, it is partial credit. So if you get the answers, error carry forward is, I think, your answer. So if you got as long as you use the same thing and work the way through and you got the next part right, then you're maybe okay with there. But this problem 1, you use problem 1 answer in this case to actually use problem 2 here. So you needed to know the max velocity of that wheel, of the motor, and that will make the graphs a little better this year, so you actually can read it. So there was around, and then you could have 57, 58, I mean, depending on how you look at that, and so I grade that accordingly to what you have here. And then you got to go a line down, and so there's some room for wiggle room for in your tiles and things. Yep. Any other questions? Right. Well, I will stick around for any more. And other than that, I'll be here tomorrow as well. And so if you or send me an email or something as well. All right.
Can you go over question 2 again? I was sort of not understanding.
Yep. 2 here. So Bill's on one here, so
I got-
you got the one, okay. So here, I wanted to rotate the motor at 30 RPMs.
Mhm.
Using pulsable modulation of a 24 volt. So this is just like the one of the conveyor belt labs where we wanted to move the motor at slow, medium, fast.
Okay.
And in this case, I wanted to move it at half the speed here. And I'm assuming it's open loop, and assuming I'm getting rid of like friction or whatever there. And so I want to go from 60 RPMs to 30 RPMs.
Okay.
And so I need to slow down the motor by 50% of the system. And so my average voltage seen by the motor should be 50% of the full voltage, which is so 24 volts made to go 60 RPMs. I need half that voltage to go to 30 RPMs.
Okay.
As soon as a linear system here.
So the linear system that you're seeing is like, oh, that one point is the 60-24 and the other point is 12-30. That's what that linear system is.
Yep, yeah. So this is a linear relationship. So yeah, this is 0 RPM is the and then maxes out at a duty cycle there. And then it's a nice linear relationship. There's no curvature or anything as well. So you could assume that 24 is wide open, and you can assume that 0 volts is stop.
And then what's the graph right underneath it?
So this is just representing like as the pulses get larger, then the average voltage gets larger. Yep. Because it's on more of the time than it's off, so it's gonna get more average voltage to that particular motor. And so if you just think about it, if you turn things on real quick and turn it off, then it's gonna have less average voltage than leaving it on more than off. If we leave it on all the time, then it's gonna be 24 volts and it's gonna be at the max RPM. And so the duty cycle is the percentage of high versus low. In this case, and then that's where you figure out how much this is spike to actually run that certain RPM.
So just to recap, it's on Thursday, normal class time, you get one page, one side.
Yeah, Thursday, normal class time, so the hour and 15 minutes. One sheet of paper, front side only, calculator. I will give plenty of space to write on the exam itself, but I will have an extra sheet of paper if we need that as well. And closed books and no laptops and things.
But we on that one sheet, like one side, we can have whatever.
You can have whatever you want to have on there you think that's needed, but it's up to you. Put your sheet together.
Do we have to get a specific calculator for the exam?
I mean, it just has to be a basic. I mean, no cell phones for like. There's no whatever you want to bring that you want to add to multiply whatever that is, but yeah. All right.